In the last video, I talked about composite analysis in the longitudinal direction for unidirectional continuous fiber composite. In this video, we will see the analysis for transverse direction. A continuous long fiber composite is weakest in the transverse direction. So by transverse direction, we mean perpendicular to the length of the fiber. Along the length of the fiber, we call it longitudinal direction. Perpendicular to the longitudinal direction, we call it transverse direction. So in this video, I will do the analysis for finding out mechanical properties like modulus for the composite in transverse direction. Let me use the example of a bamboo fiber to clarify what we mean by the longitudinal direction and the transverse direction. We can peel out these bamboo fibers quite easily along the length. You will see that the fibers are very strong in the length direction, which we call the longitudinal direction. The fibers can easily be peeled off if we apply force in the transverse direction. So this is the schematic picture of a long fiber composite in its transverse direction. So force has been applied in perpendicular to the fiber length direction. H is this height, and A represents the cross-sectional area of this surface, which is not visible to us. This is perpendicular to this surface. So that is the cross-sectional area. So just to show, in this small cuboid, this surface or this side, this face of the cuboid is represented here by this. So we can see that the fibers are running along this direction. If we see from this side, so what we will see is the cross-section of each fiber. So on this side, we will see the cross-section of each fiber. So assuming that these fibers are very uniform in size and cross-section is circular, so we will see this kind of the cross-section of the fibers. Now these fibers may not be homogeneously distributed. Now for our analysis, in this analysis, we assume that the fibers are not distributed in this way, but rather they are in a layered form. So that means from looking from this side, we will see the layer of these fibers. So this layer corresponds to this layer. So this one is visible on this side, and on this side of the surface, this one is visible. So essentially, we have a layer of matrix, then a layer of fiber, then a layer of matrix, a layer of fiber. In this way, it is arranged. So this is the kind of schematic we will use for our analysis. So now first we will do the equilibrium of forces. So Fc, which is the force on composite, is equal to Ff, which is the force on the fiber, and Fm, which is the force on the matrix. Because in this case, we are assuming this layered arrangement. So therefore, whatever force we apply on this composite will be the same force experienced by each layer, because they are essentially not sharing the load. Each layer has to take the load. The fiber will take Ff, which will be same as Fc, and the matrix will also take the load Fm, which will be same as the Fc. So it's almost like a chain where each link, if we pull the chain, then each link has to take the same force, because each link is supporting that load. They are not sharing it. So similarly here, they are in a linked way, linked to each other. So this is our equilibrium of forces, force balance. we can write in terms of stress, force divided by area. Now area will be same for each, because this surface which is not visible in this cuboid, this is the surface. So area is same for the fiber or for the matrix and for the composite. So area is not changing. So therefore this relation can be written in the form of stress. Stress on the composite is equal to stress on the fiber is equal to stress on the matrix. So these are the two relations. So we will use this relation 4.17 later. Now from the geometry of deformation, we can say the strain, total strain in the composite is equal to strain in the fiber multiplied by the volume fraction of the fiber plus strain in the matrix multiplied by the volume fraction of the matrix. Now again, since it is in a layered way, that means linked to each other, the strain will be each layer will experience its own strain, and the total strain will be sum of the strains in each layer. So we can sum them together, the strain in the matrix and strain in the fiber. So if we sum them together, that becomes the total strain of the composite. So that's why we have written here strain in the composite is equal to strain in the fiber multiplied by volume fraction of the fiber. So according to how much volume fraction of fiber we have, the fiber is contributing to the strain, and according to the volume fraction of the matrix we have, matrix is contributing to the strain. So that's why strain in the fiber is multiplied by the volume fraction. So if there is no fiber, VF is 0, volume fraction is 0, then this term will be 0, and the total strain will be basically strain in the matrix. If VF is 0, then VM will be 1. So this is how we find this relation based on the geometry and based on our assumption that this composite is in a layered form. The stress-strain relation can be given as this. Strain in the composite is equal to stress in the composite, that means the overall stress, and this is the overall strain, divided by the modulus in the transverse direction. So now we are talking about modulus in the transverse direction. In the previous video we talked about modulus in the longitudinal direction. So this is the modulus of the composite in transverse direction. Individually we can write epsilon F, which is the strain in the fiber, is equal to stress in the fiber divided by EF, which is the Young's modulus of the fiber. And similarly we can write for matrix, strain in the matrix is equal to stress in the matrix divided by EM, which is the Young's modulus of the matrix. Substituting equation 4.19 into 4.18. So these equations we can substitute here for strain values, and we can write this one. So here we replace this one is equal to strain in the fiber we get from here, and similarly strain in the matrix. Now previously equation number 4.17 we have seen that the stress in the composite is equal to stress in the fiber is equal to stress in the matrix. Therefore these stress terms can be cancelled out. So we can write 1 over ECT, which is the modulus of the composite in transverse direction, is equal to volume fraction of the fiber divided by the modulus of the fiber plus volume fraction of the matrix divided by the modulus of the matrix. Finally, we can write this equation in this form. The modulus of the composite in transverse direction is given by this relation. So this is the relation we can use for transverse direction, and we have already done the analysis for the longitudinal direction in a previous video. So generally this is the accepted form of equation for transverse direction. Now there are some analysis and models present which we can just review. So here is the modulus of the composite as a function of fiber volume fraction. So modulus is in gigapascal, and this is the volume fraction. And for longitudinal fiber alignment, we have seen the rule of mixture, which is basically a linear relation. So starting with zero fiber volume fraction, we can say the modulus is same as the modulus of the matrix here. And for volume fraction, fiber volume fraction of 1, we have the modulus which is equal to the modulus of the fiber here. And we can connect these 2 points by a straight line, and this gives us the longitudinal fiber alignment modulus in the longitudinal direction, ECL. So this is straightforward, a straight line, a linear relationship. If we plot the transverse modulus, equation 4.20, then it will give us this kind of relationship. That means for much of the volume fraction, actually there is not much strengthening in the transverse direction. Only when we have very high percentage of fiber beyond 0.9, then we see there is a sharp rise in the modulus. And basically as we approach 1, that means only fiber, no matrix, the modulus is equal to the modulus of the fiber. So this is the way we can see the relation. So in the transverse direction, we do not have much strengthening, whereas in the longitudinal direction, the strengthening is achieved all the way through, starting with very small percentage of volume fraction of fiber to the very large volume fraction. Now some people have given models for transverse direction, and one model which is very popular and used is called Halpin PSI Model. Halpin PSI Model also gives us the ECT, which is the modulus of the composite in transverse direction, by this model. Halpin PSI Model, which is an empirical relationship, gives very close to the actual values, rather theoretical values. Inaccuracies arise due to the random distribution of the fibers rather than layered, and mismatch of the Poisson's ratios of the fibers and the matrix. So in actual values, when we do the experiments, we can find that the fibers are actually not layered, they are in random distribution. So those kind of inhomogeneous distribution may cause some inaccuracies in our results, but these are basically the theoretical values, and Halpin PSI model is based on empirical relationship. The empirical relation by Halpin PSI is provided by this relation. So this is a very simple relation and it is quite popular. So here the modulus of the composite in transverse direction is equal to EM, which is the modulus of the matrix, multiplied by this parameter, where zeta is a measure of the reinforcement geometry or the aspect ratio, and it can be taken 2 for the transverse tensile modulus. Zeta is equal to 1 for shear modulus. So in our case, we are talking about Young's modulus or the tensile modulus. So therefore, we will take zeta as equal to 2. Beta is given by this relation. So here we can see that the ratio of the modulus of fiber and the matrix minus 1 over ratio of the fiber over matrix plus 2. So this is the relation which defines beta. So by using this equation, it is possible to calculate the Young's modulus of the composite in transverse direction. There are some other relations as well. For example, Bintrop has given this relation, which is very similar to the relation we have seen through our calculation. So here only the EM of this has been replaced by EM dash, and EM dash is given by this relation. So similarly, there are some other empirical relations as well, but by and large, Halpin PSI model is used extensively. Now here we have got a graph of normalized transverse modulus. So transverse modulus divided by the modulus of the matrix. So we have normalized this, and here modulus ratio EF over EM. So here we will compare Halpin PSI calculation with Adams and Donner's calculation for transverse modulus using. So the Adams and Donner's have calculated transverse modulus using finite difference method and numerical calculation, which is given in this paper by Adams and Donner. So Adams and Donner have calculated using finite difference and numerical method this type of graph for normalized transverse modulus as a function of the modulus ratio for fiber and the matrix. And here we have got fiber volume fractions, very high volume fraction of the fiber, 0.78, and here very low volume fraction of the fiber. Now on this calculation, if we plot Halpin PSI model calculation, so for 0.75 volume fraction it gives here, whereas for 0.55 it gives very close to the calculation done by Adams and Donors. So it is seen that Halpin PSI model is quite accurate, perhaps up to 0.7 volume fraction of the fiber. Beyond that, it may not be very accurate. So this graph has been taken from, is based on the figure 1 in Halpin's and Cardo's paper, which is referenced here. Using simplistic mechanics of materials approach, the shear modulus G12 for the composite can also be given by the relation. This shear modulus is actually on the plane perpendicular to the applied force. So this shear modulus is on the surface of each layer. So this also can be given by a very similar relation that we have followed for the Young's modulus. So 1 over G12 is volume fraction of fiber divided by GF plus volume fraction of matrix divided by GM. So GF is actually G12F. So shear modulus of the fiber in the plane, which is normal to the applied force direction, and GM is the shear modulus of the matrix. So finally, similar to the Young's modulus equation, we can give the shear modulus equation G12 as this one. A further modification of equation 4.25 was given by Halpin PSI as this one. So again, if we want to calculate the shear modulus of the composite for transverse loading, then we can use this relation to find out shear modulus. In this table, we have some actual data for elastic modulus, which is the Young's modulus, and shear modulus of some composites. So here we have got E-glass and epoxy composite. So E-glass is a type of glass fiber and epoxy is the thermoset. So here with volume fraction of 0.6, the longitudinal direction composite shows Young's modulus of 40 gigapascal, whereas in the transverse direction we have got only 9. So you can see a very big drop in the value. So most of the strengthening we will see in the longitudinal direction. In the transverse direction we do not have much strengthening. And G12, the shear modulus is 4 here. E-glass and polyester with 0.42 fiber volume fraction, ECl is 32, and again in the transverse direction the modulus is only 7. Similarly for Kevlar, carbon epoxy, carbon high modulus epoxy. So all these composites, we can see that in the longitudinal direction we get very high strengthening and the modulus is very, very high, whereas in the transverse direction the modulus reduces. Strength of a continuous fiber composite in the transverse direction. Last time we studied the strength and modulus in the longitudinal direction. In this video we have studied the modulus in transverse direction, and let us see how we can find out the strength in transverse direction or some other directions. If the composite is like this and we are applying the stress along the length of the fiber, in that case the strength will be given by the rule of mixture, which we have studied before. So this rule of mixture will account for the strength of the composite in this direction. But if we are applying the force in this direction or stress in this direction, then we need to find out the strength of this composite in this direction, and this direction is called transverse direction. Practically, the strength of a composite in the transverse direction is less than that of the matrix, and common assumption is sigma Ct, which is the strength of the composite in transverse direction, is equal to sigma m over 2. Sigma m is the strength of the matrix. According to our practical assumption or practical knowledge, the strength of the composite in transverse direction is very low. It's even lower than that of the matrix. The reason being, if we are applying the stress in transverse direction or this direction, then any crack can easily penetrate and it can easily grow along the matrix. It will not meet any of the fiber on its path. So that means the fracture can easily happen. For example, if this is the case, then the crack can easily divert itself and go along the matrix only. And another point is that in this kind of heterogeneous system, there is much anisotropic in the system, and therefore some defects, some voids may be present, as well as the interfacial bonding between the fiber and the matrix may be weaker. So because of many reasons and possibility of the crack going through the matrix, the strength of this composite in transverse direction will be even lower than the strength of the matrix itself. So right now we do not have any equation, but we can assume that the strength of the composite is very weak in the transverse direction. Now, composite strength with different fiber orientation. So in the first example, we had longitudinal direction and we calculated the strength in the longitudinal direction using the rule of mixture. In the second case, for the transverse direction, we have seen that the strength of composite is half of the strength of the matrix. So between these two extreme values, how can we find out the strength of the composite in different orientation? If this is the strength of the composite in longitudinal direction, then we have this direction, and 90 degree to that will be the strength of in the transverse direction, for example. Then for any angle theta, if we want to know the strength of the composite in this direction, and this direction is making an angle of theta with the length direction, this is the longitudinal direction or length direction. So if I want to know the stress at any angle theta, sigma c theta, then we can use this equation. So this equation was proposed by S.W. Tsai in this work, and using this equation we can find out strength of the composite in any direction of this composite. This is the length of the fiber, along the length of the fiber. This is sigma c theta here, and what we need are these sigma cl, which is the strength of the composite in longitudinal direction, sigma cs, that is the shear strength of the composite, sigma ct, which is the strength of the composite in transverse direction. If we know these three parameters, then we can find out sigma c theta for any angle theta. Here we have got some data on tensile strength in longitudinal and transverse directions and shear strength of unidirectional continuous fiber composites. So the matrix is epoxy for all of these cases, and these are the fibers used: boron, e-glass, carbon, and another type of carbon. The volume fraction of the fiber is 0.5. So these are the values of sigma cl, sigma ct, and sigma cs. All are in megapascal. So using this data and using the equation just now we have introduced for finding out the strength of the composite in any direction relative to the length of the fiber direction, we can use this equation and we can find out. So let us do the calculation for these data we already have, and after doing the calculation we have found that this is the type of curve we will obtain. So sigma c theta in megapascal and with respect to the angle theta. So at 0 degree theta, this is the longitudinal value, which is this one. This is along the length direction of the fiber. And for theta equal to 90 degree, this is the transverse direction, which should be this value. And all in between, we can find out the value of sigma c theta at any angle. So this is very useful equation, and this is empirical but very useful equation for obtaining the strength of the composite in any direction. Now, in order to obtain more uniform property of composites, we use the composites in laminates form. So property control in any direction through laminates. So basically different laminates are used. They are stacked together and they are cured under high pressure. So this way we can get more uniform properties. So laminates of fiber fabrics. Often they are used in the form of fabrics rather than individual fibers, are laid one over another to achieve same properties in any direction of the plane of the fabric. So within the plane of the fabric, we can obtain almost isotropic kind of properties, but across the fabric plane, the property will not be isotropic. Typically, the fiber direction is alternated by 90 degree, which is known as cross ply. So when one layer is laid and the second layer, the length of the fiber direction is 90 degree to the first layer, then it is called cross ply. So here we will see the example. So this is one ply. So this is how the fibers will look like. And to make the two ply, if we overlay the second layer at 90 degree to the first layer, then it is called cross ply. Two plies in cross ply stacking. There can be many other ways we can stack the laminates. For example, we can stack the second layer at 45 degree to the first layer. So this is also possible. The purpose of these lamination is basically to obtain more uniform properties of the composite. So here I have got this model of fibers. So here there are two laminates. So one laminate with fibers along this direction and another laminate with fibers along this direction. So if I put them two laminates one over another and with their longitudinal axis same, then this makes a uniaxial fiber composite. But if the second layer is rotated by 90 degree, so in this case we make a bilayer of composite. This is also called cross ply. So here the two layers have orientation at 90 degree to each other. Similarly, we can have any orientation. So the second layer can be oriented at 45 degree or any other angle we can choose. So the most common is at 90 degree cross ply, so that the properties, the mechanical properties of this composite in this direction and in this direction will be more or less same. So it gives isotropic properties on one plane of the laminate. But between the laminate there will be some weakness, because such kind of composites will fail by fracture between the laminates. So the cracks will initiate at the interface between two laminates. Now it also depends how we apply load. So for example, if we have this kind of orientation of the layers, and if we apply force, the maximum tensile stress in this direction, then we get full strength of these fibers, because these fibers are longitudinal in this direction. But these fibers will be transverse because we are applying the stress in this direction. So these fibers may not contribute that much. Now if we apply the force in this direction at 45 degree to both laminates, then in that case this composite will show a weakness, because none of the fibers are aligned in the direction of the maximum tensile load or maximum stress. Therefore they will not be able to contribute to the strengthening, and therefore this kind of composite will be weaker in this direction. So it all depends upon how we stack the laminates together and how we apply the force. So before designing composites, we should check where the maximum load is, maximum stress, and we should design the composite such that the most of the fibers are aligned in the direction of maximum load or maximum tensile stress. For the same fiber volume fraction, there is drastic decrease in the modulus and strength from single ply to 2 plies as the interface become the weakest zone where the fracture initiates. So if the composite is single ply, that means all the fibers are oriented in one direction, then it has got the maximum strength in this direction, in the longitudinal direction. For 2 ply and more than 2 plies, basically the interface between adjacent plies will have weakness because of some defects, and therefore the strength property will go down. For multi-layer laminates, the layers should be stacked symmetrically on both sides of the central plane. On both sides of the central plane, we should stack the laminates in more symmetrical manner with respect to the orientation of the fibers. Moduli of cross-ply laminated composite of boron fiber in a polymer. So here we have got some data to compare. So 1 ply and stress in the longitudinal direction. So this is the first case where it is a single ply. All fibers are in 1 ply and the stress is being applied longitudinal direction, length direction. In that case, we get a very high tensile modulus. Compressive modulus is also quite high, and this is the shear modulus. 2 plies at 90 degrees to each other. So this is the example of cross ply of the same polymer and same volume fraction. The stress along the longitudinal direction of one of the layers. In that case, we see that the tensile modulus is drastically reduced, almost half. Compressive modulus is also reduced. Shear modulus has increased to some extent. Now 2 plies at 90 degrees to each other and stress being applied at 45 degrees to the longitudinal direction of each of the layers. So now the 2 plies are in the cross ply orientation, but the stress is being applied at 45 degrees to both of them, both of the layers. So in this case, the tensile modulus has reduced considerably. Similarly, compressive modulus also has reduced, but we see that shear modulus actually has increased. So stress and strain property of a cross-ply laminate will show something like this. This is a schematic representation, and what we see is a kink here, and this kink happens because one of the layer, the 90-degree layer, cracks. When the crack initiates between the layer which is aligned in the direction of force and another layer which is 90 degrees to this layer, there is a crack. So there is a failure at the interface. And at this situation, basically the layer which is aligned in the direction of load takes all the stress, and the layer which is 90 degree angle actually does not take any load. So we can see this kind of stress strain behavior for cross ply laminate composite. We should also remember that in composites, the complexity arises not only because of the heterogeneity, there are 2 or more than 2 materials inside, but also there are possibility of different defects. For example, voids can be defects as well as moisture. These composites are very prone to take moisture inside because the moisture will penetrate inside the material because of the interface between the fiber and the matrix, and these moisture can actually reduce the strength and modulus of the material quite considerably. So these are the possibility that the materials can be weakened in service. Let me summarize the main points. Modulus and strength of an unidirectional continuous fiber composite in the transverse direction is lower in comparison to those in the longitudinal direction. Strength of an unidirectional continuous fiber composite in the transverse direction is even lower than that of the matrix. We can calculate the strength of the composite in any orientation with respect to the longitudinal direction using an empirical relation. In order to obtain near isotropic properties of a composite in one plane, composites are often made by stacking layers of fiber in fabric foam. However, the mechanical properties can still be different in different directions. Laminated composites are weaker at the interface between two adjacent laminae. Thanks for watching this video. If you have any question or comments, please write them down below in the comment section.